going to present here some joint work with Alice Smilgins. It's about optimal mergers and sector restructuring. As you know, I've worked a lot with regulators and quite often to determine the efficiency of firms in natural monopoly industries, for example, and to set allowed revenues for such firms. But sometimes they ask me, can't you find any additional savings that we can impose on the firms? What about consolidations? And we've done that in several studies, and we typically just look at some pairs of possible mergers. And as illustrated over to the right here, you can see in the red box here, several merger pairs, many hundred merger pairs in the Danish water industry that would lead to additional savings beyond individual earning of more than 10%. Of course, we realize you can't just merge all firms because some mergers may exclude other mergers. So we also played a little bit with that by looking for roommate solutions or assignment solutions. So in roommates, we look for pairs of firms that should merge and have incentives to stay in the mergers that we propose. In the roommate, we ignore the incentives and just find the optimal combination of pairs in the industry. But it's all a little bit ad hoc, and the question is, could we address this in a more systematic way? It's relevant in general because sometimes structural inefficiency, the question of whether you have the right number of firms of the right size in an industry, can be just as important as individual inefficiencies that we try to eliminate in many projects. So if we want to do it more systematically, we run into 4 challenges. One is that we have to calculate the merger gains. And this can be done if you have a cost function. It's relatively easy. You can just calculate it as illustrated in the lower formula here. But if you do not have a specific formula for the cost function, you can use DEA, for example, or linear programming. You can calculate it like we've done in the Bogetoft bank paper many years ago, and which has been used in many other papers since then. So the idea is basically to ask the mergers of firms in set H. They are using combined input here, and they're producing the combined input of Y's in the second line here. And we're asking how much could they have saved if they adjusted to best practice as determined by the original firms. So here we use a slack formulation. Normally we use like a Farrell efficiency formulation, but it's all the same. So the question is basically how much can we save by merging firms. The second problem is that there's in an industry a ton of possible mergers. In the empirical example, we look at 39 firms, and what we see is that it leads to more than 500 billion possible merger combinations. So there's a sort of a size problem to be dealt with. The second or the third problem is that some mergers may exclude others. So if you merge A and B, you cannot at the same time merge B and C, unless you of course create A, B and C as a merger. So there may be some mergers that are excluding each other. So basically the problem we have to solve is a combinatorial optimization problem. If we say that script P of I is the set of possible subsets of the original firms, we must find a subset of this set of subsets that includes only mutually exclusive mergers, as indicated here in the constraints. The last problem that we also have to deal with is the fact that one thing is that the regulator can propose a merger restructuring of the sector, but the individual firms may not have private incentives to participate in that. So we need to think also about incentives and the allocation of the gains from these mergers. In the paper, we suggest 2 ways to do it. One is a so-called one-step approach, where we basically formulate one mixed integer linear programming problem that integrates the DEA estimation of merger gains and the merger selection. We also have a multi-step approach where we basically pre-screen the feasible mergers, come up with a set of relevant mergers, and then we just combine them in a set packing problem. And in addition to all of this, we also show in the paper how you can, by adding extra incentive constraints, get to stable mergers. The one-step approach is illustrated here. It's a big mixed integer linear programming problem. We basically have to find a set K of the mergers that are non-overlapping, that maximize this total sum here. In this formulation, the x and y's are the inputs and outputs of firm I, and in the empirical application we only look at the inputs after having eliminated individual saving possibilities, so they're basically projected to the frontier. MIK is 1 if firm I is in merger K, and the lambdas are the usual ones we use to determine the point at the frontier we are comparing to, and SK is again the saving in merger number K. So basically what we're doing here is that we are summing for a given merger, we are summing over all the inputs of the firm in that merger, and similar down here we're summing the outputs of all the firms in that merger, and then we find out how far is that from the best practice frontier, and that distance in an additive way, that becomes the savings. Of course, we have to make sure that a firm is not participating in more than one merger, and that's what we formulate down here. So for a given firm I, we sum over the mergers in this structure, and then they should not be able to sum to more than one. Sometimes we also introduce a discordance index. So basically we say that some mergers, some pairs of firms cannot merge together. So, and then the discordant is 1. And then you need some constraints saying, for example, that if I and J cannot merge, and if J is in a member of merger K, then I cannot also be a member of a firm of merger K. So that's basically the formulation. This, you can't see all the conditions out here, but it's basically saying that for any I, J, and K, this must hold. This works okay if you have a limited number of firms, say 50 to 60 firms, and you can run it with up to 10 mergers on standard software and hardware. But if you want to investigate like 20 mergers, it becomes really, really slow and time consuming. So in that case, we think it's better to move to a multi-step approach. I want to illustrate one feature here, that is basically that if you start calculating the gains from having one merger, 2 mergers, 3 mergers, it's going to weakly increase, but it may be stable at several levels, and then only later may it actually increase the total gain from the merger. And that's basically illustrated in this picture here. The multi-step approach is simplified in the sense that you use some kind of heuristic or systematic way of enumerating all possible groups that satisfy any kind of discordance index, and then you calculate the value of doing those groups or mergers, and if it's a negative, which it might easily be if you have a variable return to scale, they may end up being too large, for example, then you just discard those mergers. So you end up with a subset of all the mergers which is relevant. And then if we assume that there are m such feasible relevant mergers, we let set K be the indicator of whether we should choose merger K or not. And again, we use MIK to be an indicator where every column shows for the different mergers which firms are part of that. And then we must select the best non-overlapping subset in the sense that they generate the highest possible mergers. And the fact that a firm can only be part of one merger is given by these constraints here. So it's a set packing constraints, relatively easy to solve. If you have 39 firms, in our case, we end up with having only 599 potential realistic mergers, and that is solved in less than a second. Last problem is stability problems. The central planner may find the optimal mergers, but the firms may resist to implement them. So basically, we want to make sure that no groups of firms can deviate and make all firms better off. So that basically has to do with how should the gains from the merger be shared among the firms. And of course, you get more bargaining power in such a negotiation if you have more outside options. And that's kind of illustrated here in figure 3, where you have 3 firms. If 1 and 2 merges, they gain 50. If 2 and 3 merges, they gain 40. So this, you want to implement 1 and 2, the merger of those. Excuse me. If you want to do that in a stable way, you need to ensure that firm number 2 is getting at least 40, because if he gets less than 40, he can always convince firm 3 to merge, and then he can extract 40 or very close to 40 minus epsilon. So here's there is a stable merger. You can implement the ideal merger here, but it requires that the payoff to firm number 2 must be no less than 40. Sometimes you can't find a stable solution, or sometimes introducing stability constraints will lower the total value that you can create. An illustration where you cannot find a stable solution is given down here. You can't exactly see it because of this picture but there's actually 3 firms here, DMU 1, 2 and 3. You get a gain of 100 here, and all the other 2, 1 and 3 and 2 and 3, they create a gain of 80. So it's clear that you cannot find a division of the 100 such that neither firm number 1 and firm number 2 wants to deviate. If you split it equally, for example, they each get 50, but then they could just switch to merging with firm number 3, and then they would get up to 80 instead. If you want to introduce this into the multi-step model, you have the original multi-step model here, but then you need to include some extra variables for how to divide these merger gains. And if a merger is implemented, we need to make sure that the shares that the different firms inside that merger is getting is equal to the savings from that merger. And if a merger is not implemented, so set k is equal to 0, then we need to make sure that what they get inside that what they are already getting, the sum of what they're getting, those that should participate in k, is more than what they could actually get by introducing merger number k. So that's basically the constraint. And then in addition, we need to make sure that all the sums of all that's actually a redundant constraint, I would say, because it basically says that the sum of all the gains that are divided is equal to the sum of all the gains that are produced. But that kind of comes from the second set of constraints here. If you introduce these constraints, sometimes the problem does not change. All good. The best solution is also incentive compatible. Sometimes it drops, and it means that you need to give up some of the synergies in order to get a more stable solution. In the application, we studied some Danish electricity distribution companies. If you look at the individual inefficiencies, they're quite low. It's a very, very simple model with only 3 cost drivers and big savings here. So you can say that the traditional focus on individual efficiency is well argued here, if you look at what we can gain later on. But if you now want to look at what can be obtained in terms of pure scale and scope effects from mergers, we solve the various problems, And here I have for the variable return to scale context, if you allow one merger, it will generate the best possible merger is generating a saving of 16 million, and you can see which firms participate. There's 5 firms in that. If you introduce 2 mergers, the sum of the mergers increases to 22.9. It's more or less the same group. A couple of firms is leaving the first group and move to group number 2, and then some extra one comes in. So they switch around a little bit, but you end up having this configuration. The illustration here shows that, for example, these 2 reds should merge. These 2 this and this should merge. So there's a few mergers here that you should be implementing. This illustrates the 5 merger solution. If you now introduce distance constraints, you get, of course, smaller saving possibilities, and it's illustrated here. So this could be a very good example of a discordance. As I said, discordance could also have to do with ownership structure or with management style or something that prohibits 2 firms to actually merge. If you have increasing return to scale, you get, and you only allow mergers within 50 kilometers, you get many different groups illustrated by the different colors here. And you see, for example, they have 4 firms merge here, the yellow one, 2 firms merge here, the purple one, and so on. You get a total saving of 16 million in this way. We first did this solution, and then we said, okay, now let's introduce these stability constraints, and then we get these payoffs here. And then you can check that it doesn't change the value of the program, so we know it's for free. You get stability, you can say, and we illustrate in the paper why some of these firms are not involved in any merger, because they are already getting more from the mergers they participate in. Here you see that when you allow for more and more mergers, more and more distances, you get more and more possible groups to consider, and you also get more savings. But already at 75 kilometers, you're getting almost the maximum saving you can get in this industry here. So what have we done in this paper? Well, we have introduced these methods. There's of course some extensions that can be relevant. One being that you could have multiple inputs instead of the single input, namely cost, that we used in this paper here. The many possible mergers we are dealing with and are having problem with in the one-step approach could also be dealt with maybe by solving it using a column generation procedure. I think there are many possible applications of these approaches. And at least for a regulator, it can help quantify and give some evidence for some kind of what kind of consolidation potentials are available, which is much more informative than the one we used to present, as I showed in the first slide. I want to make a note here also that many revenue cap regulations is actually discouraging mergers because of the convexity, but we can talk about that. That basically means the regulators need to think also about how they should in a clever way deal with so-called merger remedies. To sum up, we have 3 methodological contributions: a one-step approach, a multi-step approach, and then ways of checking for stability. As I said, many possible applications, because there are many cases where it doesn't make sense just to reorganize by looking at scale efficiency, for example, and then just say that basically if you have increasing return to scale or non-decreasing, you should basically end up having one company that serves the whole country. If we're talking district heating, water, gas distribution, hospitals, courts, bank branches, and so on, proximity to customers matters a lot. Last note is that these discordance constraints, these constraints about what is actually allowable mergers, they help reduce the computational burden tremendously, but they do also make it easier to get stable solutions. So that's an important takeaway. Okay, that's it. Thank you very much.